Okay guys, what I want to do is I want to show you guys a very, very cool formula that you can use almost in any physics, mechanics problems, okay? The only time you cannot use it is with collisions. Okay, so when we do collisions, there's one of two formulas that apply. When we do collisions, it's either preservation of momentum, and who can tell me what is the law of conservation, not preservation, sort of. Okay, conservation. What is the conservation of momentum theorem?
Isn't that energy cannot be destroyed? No, that's the one.
The total linear momentum is the total
Linear momentum of an isolated system is conserved.
Where I don't know, external forces acting.
What about the total momentum?
It's conserved.
It's conserved.
Just before collision, after collision, where
Right. So in other words, we write it like the total momentum, that means the sum of momentums before, so in other words initial, is equal to the sum of momentums after. Okay? So that is conservation of momentum. It is actually very easy. If you've done the questions on the course, if you can do them, they really cover all of the type of questions that you really can get. The next one is elastic collisions. Okay, so an elastic collision. Who knows what an elastic collision is?
when kinetic energy is conserved.
That's when kinetic energy. Now, conservation of momentum is a universal law. It always applies. Okay, an elastic collision is the conservation of momentum still applies.
Is that equal to something?
But in an elastic collision, the sum of my kinetic energies before is equal to my kinetic energies after. Now you need to know that momentum is mass times velocity, and then you need to know that kinetic energy is half mass times velocity squared. So you'll take every element in that system, mass times velocity, add them together before, add them together after, and it has to be equal, always has to be equal in an isolated system. An elastic collision is if they tell you it's an elastic collision, then you take half mass times velocity squared for everything, and it has to be equal, okay? So that is in collisions, we use these theorems, but the formula that I want to show you, you actually know it very well, but no one is using it, so I'm going to focus a little bit more on it and show you how you can use it in almost any system. Okay, that is this formula that the net work done is equal to what? This is the work energy theorem.
It's friction force, it's force times distance, isn't it?
Yes, but that's the definition of work. In other words, work itself, any work applied, work done by friction, work done by gravity. So I'll get to that in just a minute. But this is the work energy theorem.
Isn't it that it has potential energy and kinetic energy?
Doesn't it have cos theta somewhere?
No, it doesn't.
It does have cos theta in the original formula.
Okay.
But what is the work energy theorem?
Gosh, the network is equal to the total kinetic energy.
No, it's equal to the change in kinetic
Change,
energy.
yes.
Okay, now let me explain this to you guys. It's not difficult. It's really, really, really simple to understand. Okay, I'll explain it like this. Where do we use the concept of net very regularly? What does net mean? If I talk about something, a net, where do we often use that concept?
With forces.
Outside of physics.
Besides physics,
No.
isn't this coming from internet? There's net.
I don't need to laugh. No, you're 100% right.
There's this this other message I got from what the home is like. I was getting free airtime. It said surf the net.
Surf the net. You're
That's what
100%
I'm
right.
saying.
That is called, it's the internet is shorthand called the net. So you are right, but that's not what this word is referring to. Net. Can you think of a place where we often talk about net something? Net never comes on its own. It's net something.
Network.
Okay, wait. Let me answer because you guys are going to embarrass yourself soon. No, but this is funny. Network done. Anyways, no. Net. Have you ever heard of net profit? Net income?
Oh,
Net. Now, what is net
financial.
income? What is your net
The
income?
total
This is
income.
some-
No.
No, I mean total profit.
It's profit. Net income is your profit. Now, what does that mean? What is profit?
What you got
Minus
initially
the
extra.
expenditure.
Sorry?
Yeah.
What
What
did
you
you
got
say?
extra from the original amount. What you.
Almost. It's what you get extra. What you do is you take your income minus your expense. Does that make sense? So let's say my income in a month is 10,000 rand, but all my expenses add up to 8,000 rand. Then my net income is 2,000 rand. My profit is another word for net income. So net talks about what you get in minus what you get out. So when we talk about net work, work is the ability to convert energy. Okay, so you can think of work as energy that's being converted. Okay, so think of work as energy. So if I talk about the net work done, it's talking about the energy that is left. Now let me explain by drawing for you a little diagram. Let's say we have an object here that's being pushed up an incline. Okay, we're looking circle, but this thing is being pushed up an incline. What do we call the force when something is being pushed? It's an applied force. So an applied force, this is applied. Applied force is always either a rope or an engine or a man pushing. Is that how you spell engine? Or a man pushing or pulling, or it is something that's being applied. Does that make sense?
Yes.
I'm applying a force. That's an applied force. Now, if we talk about this is always an income. No, I lie. I'll take that back completely. Okay, this is an income energy. So when I'm applying a force, I'm adding my energy into the system. Okay. Now, it can only be an income if it's in the direction that the object is moving. You understand? So the object is already moving in a certain direction. Let's say I'm pushing the object upwards and it's moving upwards. Okay? Now, if I'm pushing in the same direction as the object is moving, I'm adding energy into the object. Does that make sense?
Yes.
Okay. So in other words, my work, the income here would be work applied. That would be one of the incomes. Now, what other forces are acting on this object?
Frictional force?
Frictional force. Frictional force is always in the direction or in the opposite direction?
Opposite.
Always in the opposite direction. So here we have frictional force acting on the object. The work done by friction. Okay, so what do I mean by the work done by friction or the work done by the applied force? Well, work itself is the formula. Any work done is that force. Whatever the force is, if it's force applied, it's force applied. If it's friction, it's friction. If it's gravity, it's what do we call the force of gravity? You don't know?
What is the force of gravity?
Yeah, what do we call the force of gravity?
It's the force that you exert due to position of your
No, the force of gravity is called weight. weight is the force of gravity, which is mass times gravitational constant. That's the force of gravity. So whenever I'm working out the work done by a force, I take that force and I multiply it by the distance that is in the direction of the force.
Yes.
So in other words, if this thing moves from here to there and this distance is delta x, then the force done, the work done by the applied force is the force applied times the distance over which it was applied. Okay? Frictional force is the work done by friction is equal to the frictional force. And how long is friction applied on the system? Well, for as long as it's moving on a frictioned surface. Okay? Does that make sense? So times, so that's, I'm working out the work done by friction. I take that frictional force and I multiply with the distance over which that friction is applied. But here's the important part. For example, the work done by gravity is the force of gravity, which is weight, mass times gravitational constant, times, and now it's not delta x anymore because the problem with gravity is the force of gravity is always straight down. And the object isn't moving in that direction. Do you see? It's moving like diagonal. It's not moving in this direction. So but it is moving up. It is moving in the direction of the force, but not this much. If I take from this point to that point, you see, it is moving up, but not this whole distance. The distance over which the work is done by gravity is only from here to there. So we need to find out what this size here is. What is this length?
Okay.
Now, gratefully, all of you have maths, so all of you should see that this is trig, and this is an angle theta, and what side am I trying to calculate?
On the opposite side.
The opposite. So I have to use opposite. What I have this length. What do I have?
Hypotenuse.
Hypotenuse. So opposite over hypotenuse is sine theta. So if I have theta, if I know the angle that the surface is making, then I can find out the opposite by multiplying both sides with the hypotenuse. So I get that oh no, sorry, Bakani, you don't have maths. Okay.
No, I'm fine.
But you can remember this.
Yeah.
Okay. So there we go. The opposite side length. In other words, this length, the height that it travels, that's the only part where the gravitational force is doing work. He's not doing work for the whole distance of x. He's only doing work for the distance that he's picking it up on. If it was just going straight up, then delta x would be equal to delta h. Delta h is now the change in height. So if I was just picking it up from the bottom to the top, then my displacement is equal to my change in my height. If I'm just moving it from left to right, then my delta x is whatever, and my delta h is?
It's h sine theta.
No, 0. What was my change in height? Nothing. I didn't lift it up at all.
Okay.
So if I'm lifting it straight up, then delta x is equal to delta h. If I'm putting it straight on the horizontal axis, then delta h is actually 0. So anywhere in between here, delta h will be somewhere between 0 and x. It would be less than 0, it would be less than, greater than 0, it would be less than x. Okay, but how can we calculate it? We take delta x and we multiply it with sine theta. Okay, we take this, that's what I calculated here. Hypotenuse, which is delta x. Don't confuse this h with that h. They're not, this one is hypotenuse, that's height. But I take the hypotenuse, which in this case is delta x. That's the distance that my object is literally moving. But how high is it being picked up? That's there. And that depends on the angle. Okay. Make sense?
Yes.
Is that okay? So in other words, the work done by gravity is not mass times gravity times delta x. It would only be that if I was just picking it up. It would be mass times gravity times delta x sine of theta. Okay, so now let's go and look at the work done in terms of income and expenses. Okay, I'll explain the right-hand side of this equation just now. So if I put energy into a system, that would be work applied.
Yes.
Now in this case, if I'm pushing in the same direction as the object is moving, I am adding energy, so I'm at income.
Okay.
Work applied is at income.
Income.
Is the work applied by friction, there's frictional force, is it an income or is it an expense? Will it add energy or will it steal energy? It will steal energy, so I will subtract expenses. I will subtract the work done by friction. Okay? How about the work done by gravity? Gravity is pulling down. If I'm pushing something up a hill, is gravity going to work in my favor or against me?
In your favor.
Oh, really? Let's see you push up my car up a hill. Is gravity helping you or making it more difficult to push it up the hill?
It should be happening.
It should be helping you if you're pushing it up a hill.
Yeah.
So what you are telling me, it's easier to push it up a hill than to push it straight.
No,
No,
I'm not
it's
saying
easier
you-
to push it
it's-
straight.
I think you're taking it too general.
You think it?
You're taking it too general. As if you're pushing it, you know it's hard to push it up the hill.
Yeah.
Then pushing it straight.
So if it's harder, why is it harder to push it up a hill than to push it straight forward?
You said friction force is always opposite.
No, but let's say that it's the same road. If I push it straight, or I'm pushing it up, it's the same road. Friction isn't more. Friction is how difficult that surface is to push. Okay?
The roughness of
The roughness of the surface. Now whether I lift the surface at an angle or it's straight, friction won't change. What does change?
It's upward force.
I'm trying to push it up.
So the gravity will change.
In other words, if I push it straight, I'm not trying to lift the height. Do you understand?
Yes.
Gravity is not working against me, it's not working for me.
Yes.
It's neutral. That's this point. So what is the work done by gravity if I'm not changing height? The work done by gravity is mass times gravity times the change in height. Okay? Now change in height is delta sine x, delta x sine theta, but that's only if I don't know what the change in height is, then I'll use this. If I know what the change in height is, I'll just use the change in height.
But in this case, we don't have because we're not moving upwards.
But we do have it. If we're not moving upwards, delta h is
0.
0. So what is the work done by gravitational force?
Zero.
It's nothing. It's not adding energy. Even if I add it or subtract it, it's not doing anything to the system. Does that make sense?
Yes.
But if I'm pushing it up, is it taking away from the energy that I'm applying, or is it adding energy to?
It's
Taking away.
It's taking away. Does that make sense to you?
Yes.
So in other words, it's not helping me move this thing up the hill. As a matter of fact, if I let go, it will start rolling downhill. Which means if I wasn't applying a force, it would have the same effect as friction. It will be against the direction of motion.
Okay.
Does that make sense? So that means work done by gravity. Now work done by gravity can be an income or an expense. It depends on in what direction is my object moving. If I'm moving up, gravity is always moving down. So if my object is moving up, the work done will always be an expense. If my object is moving down, now gravity works in my favor. I can now put my car on the downhill. I don't even need to push, and it will start going down. Why? It's not friction that causes it to move. Friction is always in the opposite direction. What is causing it to move? Gravity. Gravity, if it's coming downhill, is an income. Make sense?
Yes.
Okay, but for this specific case, we're now looking at this specific case, we're moving something up an incline. Okay, then gravity would be an expense. Now, imagine this. Imagine I'm trying to move an object. As I'm trying to move it, I'm putting in enough energy to overcome friction. So in other words, the amount of energy that is going to be stolen by friction and gravity, I'm giving just enough energy to overcome that.
Okay.
Are you with me?
Yes.
Does it make sense?
Please repeat that, sir.
So remember, so friction needs energy. For me to push this thing, okay, I need to put in more energy than friction is stealing.
Yes.
Does that make sense? If I do put in more energy than friction is stealing on a straight road, so let's ignore gravity for a moment. If I put in more energy than friction is stealing, what will happen to the object?
Accelerate.
It will accelerate. Brilliant. If it was standing still, it will be going faster and faster and faster and faster. Very few people know that, actually. They don't get it. Okay. If I'm pushing it up the hill, in order for it to accelerate, I must overcome friction and gravity. Do you understand that?
Yes.
Okay, so what will happen if I'm making a profit? Okay. For those watching the video, I'm making inverted commas. Okay. What will happen to the object if I am making a profit in my energy? In other words, I'm putting more energy in than is being stolen. The object will
Accelerate.
accelerate. It will accelerate because what is happening with the extra energy? I'm still putting it in. What is happening?
it's
It's
not
not turning into
dominant.
heat. The thing's not catching flame. It's turning into some sort of other energy. So my energy that I'm putting in to push this thing is being converted into kinetic energy. Okay. Now, here's the one thing. So, all of the energy, so this is my profit, remember? My profit will change my kinetic energy. Does that make sense?
Yes.
In other words, if my net work done, in other words, the profit of energy I have, if that is greater than 0, then it means that my future kinetic energy will be minus my initial kinetic energy, that's the change in kinetic energy, will be greater than 0.
Okay.
Does that make sense?
Yes.
All I'm doing is I'm changing this into delta change in kinetic energy. In other words, remember what we said now, if I am putting in more energy than gravity and friction is stealing, I will be changing my kinetic energy. I will be adding, the energy will be converted into kinetic energy. And so the change in kinetic energy will also be positive. Makes sense? In other words, my future kinetic energy, just notice this is a inequality. I'm just adding EKI on both sides. And then I get that my future kinetic energy will be bigger than my initial kinetic energy. Okay. Does that mean before I started applying the force, the object wasn't moving?
No.
No, it was moving. But now I'm making it move faster. So what is kinetic energy? Is a half mass times velocity squared. In other words, half of my mass velocity squared, my future velocity squared, would be greater than half of my mass times my initial velocity squared. In other words, if I can divide both sides with a half and get rid of that. I can divide both sides with a mass, get rid of that. And then I get that my future velocity squared will be greater than my initial velocity squared. Do you see? So literally, if my net work done is positive, my future velocity will be greater than my initial velocity. Make sense?
Yes.
Okay. Now the opposite is true. What if my net work done is less than 0?
Which means you'll be putting less energy to
It
Exactly.
decelerates.
So in other words, friction wants energy.
Yes.
It's taking some of the energy that I'm putting in. Gravity wants energy. It's taking some of my energy. But now I'm not putting enough energy in. Where is friction and gravity going to get its energy from? You understand? They require energy. Friction requires energy, and friction gets all of its energy from the applied force. Okay? So it gets all of it, so friction is satisfied, but now gravity needs energy. Maybe I can satisfy some of gravity's energy, but not all of it. So gravity still wants energy based on mass times gravity times change in height. Okay? The mass still requires a certain amount of energy to push this thing up the hill. But if I'm not putting in enough energy, where is it going to get its energy from?
From the applied.
No, I'm already using up all of my energy on friction, and the little bit that I have left, gravity takes, and he wants more. You understand what I'm saying?
Yeah,
He
from
wants more.
Isn't it from
No.
kinetic energy?
From kinetic energy. So this object is moving. The object itself has energy based on its movement, the fact that it's moving. So if I'm not putting in enough energy to keep it moving,
It's gonna take.
it's going to start taking energy from the object itself. And what is going to happen to the object? It's going to?
Move in the opposite direction.
It's not going to move in the opposite direction yet.
Decelerate.
It's just going to decelerate. It's going to slow down until it reaches zero, and then probably start heading in the opposite direction. So it's going up the hill, go down. Do you see what's happening?
Yeah.
Yes.
Okay. So in other words, if my net kinetic energy, if my net work done is less than zero, then with the same, I don't want to write all this out again, but in the end, the sign will just change. My future velocity will be less than my initial velocity. You see that?
Yeah.
So the same thing applies, and this is now. So this is a remarkable formula because it literally can be used in any situation of mechanics that's not a collision. You can use this formula. Projectile motion, pushing something up an incline, working out if someone dives into water. You know, remember that question?
I do. Oh my word, that was bad.
Okay, I'll show you. We'll go through
It was
control
nasty.
test 1. We'll go through control test 1, and I'll show you how you can almost do every single question in that
Okay,
paper
please.
except for momentum, just using this formula.
Okay.
What formula? That net work done is equal to the change in kinetic energy. Now, we just need to figure out what is an income and what is an expense. So let's just look at another scenario. Let's imagine we're now pushing something down a hill. Okay, or let's say this. Let's say I'm not pushing it down the hill, but I'm in a car and I'm going down a hill and I am applying the brakes. Okay, so that it doesn't go down the hill too fast. Or you're on a bike and you're pulling the brakes so that you don't go faster and faster, so that you can go down at a slower velocity. Now, what if I'm going down a hill? Give me some incomes. What are income energies if I'm moving down a hill?
Gravitation.
Gravity this time is an income, so it will have a positive.
Yes.
What would be any more incomes? Can you think of more incomes? Is applied force an income in this case?
No.
Why not?
Because
Working against.
Yes.
It's working against motion. It's taking away from the velocity. Does that make sense?
Yes.
So we'll have minus the work done by the applied force. So if I'm pushing the brakes, something is adding a friction, like not a friction, a force. I'm applying a force. An engine is applying a force. Or do you understand that? Okay, so that's what applied force is. Plus, what is another expense?
Frictional.
Friction will always be an expense. That's nice though. You can always just subtract friction. And it's equal to the change in kinetic energy. So whatever the answer is. Now, here's a formula. So in other words, this is not a standard formula. It's not you will always use this formula. Each scenario you'll look at in a new way.
Okay.
For example, let's think of something being thrown up into the air. If I throw something up in the air, Here's the one thing that you have to keep in mind. The moment something changes, we can't use the same formula if something changes. Let me give you an example. If I throw something up in the air, here's my hand, I've got a ball. While I have the ball in my hand, just before it leaves my hand, the whole time, like at the bottom, what is the velocity?
0.
0. As I'm throwing it up, I'm applying a force to that ball. The moment that ball leaves my hand, the force that I apply is no longer acting on it. Which means there's a story now here where the ball is in my hand, and then the moment it leaves my hand, the story is now different. It's a new scenario. So we would have an initial velocity here and a final velocity there. But this final velocity will be the initial velocity for the new story.
Yes.
Do you get that? So the moment something changes, the moment a force, here's another example that we saw yesterday. Here's a ramp like that. And from here to there is horizontal. It doesn't look like that on my graph. And here there's friction, but this portion is frictionless, which means there's two stories happening here. They call this A, B, and C. So in other words, if I consider the system, I must consider two parts. This is an initial velocity and that is a final velocity, but this final velocity is the initial velocity for this system. Do you get that?
Yes.
Okay, so the moment something changes, I consider it in a new light. It's a new story. I separate the two. And the only connection is that the initial velocity here is the final velocity of the previous story. Does that make sense?
Yes.
Okay, cool. So something is rolling down here. I didn't say that. Okay, so just with that in mind, we don't just use this formula and this is initial velocity and that's the final velocity. That's not how it works. Do you get what I'm saying?
Yes.
Okay, so let me quickly go on and show you how. So imagine I'm throwing something up in the air, but I'm not talking about this part. I'm talking about something is now being thrown up the air. All of a sudden it's thrown up in the air. Okay? And what are the forces? What are the incomes and the expenses while it is in the air? So while it is in the air, we call it free fall. What are the incomes and expenses of a free falling object?
It's gravitational.
Gravitation. Is that an income or an expense?
It should be an expense.
Expense. Okay. Negative WG. Anything else?
It's normal force. Normal force.
Normal force only applies when an object is on a
Isn't
surface.
friction is also an expense?
Friction would be expense. Let's assume there's no air friction. Okay, so friction would always be an expense, but let's assume, usually with these type of questions, they say ignore air friction. Okay, so let's ignore air friction. Is there any applied force while it's in the air? No, it's left my hand. No one is touching that thing. The only force acting on it is gravity. So, awesome. Gravity as an expense is equal to what? Change in kinetic energy. Now look at how cool this formula changes. Now it changes to the work done by gravity is always mass times gravity times the change in height. Now this time we don't use that delta x sine theta because it's going horizontal.
There's
vertical.
no angle.
Yeah, there's no angle involved. It's a 90-degree angle actually. So cos theta would not apply here. Okay, so in other words, here I'm just talking about the height. The change in my height is equal to a half mass velocity squared. Now I see, both sides of this have a mass, so I can cancel out the mass. Sorry, this is not velocity squared. This is in final velocity squared minus initial velocity squared. Sorry, that's the change in kinetic energy. Let me write it like this. It's probably easier for you to understand it like this. Change in kinetic energy is future kinetic energy minus initial kinetic energy. Make sense? But now I see everything has mass. So I can divide mass with every term. And I see there's the half. I don't like working with that half. Let's multiply everything with 2. And this is a negative. 2g delta h is equal to, now I multiply this with a 2 to get rid of those halves. So I get future velocity squared minus initial velocity squared. And now if I add initial velocity on both sides, then I get future velocity squared is equal to initial velocity squared minus 2g delta h. Does that look familiar?
Yeah.
Do you see? So in other words, I don't need to go and remember this formula. Now in our formula it's a plus there, but then we must use g as a negative anyway because g is downwards. Okay, so that's fine. So we'll keep it a negative here. I just want to show you, you didn't have to go and remember that formula. You just have to remember this idea. What are my income energies? What are my expense energies? And I just always equate it to the change in delta or the change in kinetic energy. Now we'll do a few examples like this and then you'll see how it works. Okay, I just want to show you some scenarios, different scenarios, and each time the formula is different, but the idea is the same. Make sense?
Yes.
Cool. What did I want to show you? Okay, let me quickly just show you in this formula that we have here, for example, why can I use this formula to calculate anything except time and acceleration? If they ask me for time and acceleration, it's probably going to take another step. I can still use this, but it's a little bit more complicated. Let me show you. Weight done, or the work done by gravity. How did we say? What do we use for the formula for work done by gravity?
It's mg.
That's
mg delta h. Okay, or it can be mg delta x times sine theta, depending now on whether I have the height, the increase in height, or whether I only have the distance on that ramp. Okay, depending on that. Okay, and then what is the work done by the applied force? How do we calculate that? Okay, I'll show you. Force applied times delta x. The normal work formula. This is also the normal work formula. The work formula is my force times my displacement. Okay, but gravity force is weight. Gravity displacement is delta h. Weight is mass times gravity. Delta h.
Yeah.
Do you understand what I'm? They're all the same formula. What is the work done by friction?
Same
Then what?
as force applied.
Frictional force
Force
times delta
delta
x.
x. Yeah.
What is the formula for change in kinetic energy?
Half mv squared.
Half mv future squared minus half
mv initial.
mv initial squared. Think of any value. If they ask you to find the displacement, then there's displacement. Okay. If they ask you to find out the frictional force, there's the frictional force. If they ask you to find the applied force, you've got the applied force. If they ask you to find the mass, there's the mass. If they ask you to find future velocity, there's future. Initial velocity, there's initial. If they ask you gravity is a constant, if they ask you to find the height, there's the height. Okay. You see that?
Yes.
The only values that are not in here is t, time, and a, acceleration. You see that?
Yeah.
Okay. So those are the only ones that you can't necessarily get by this. But at the same time, they will give you all of the other values. If you don't have acceleration or you don't have time, okay, then acceleration is future velocity minus initial velocity over delta t. Or if you don't have t, then t is, the time is, in that formula, well, I suppose you can just use this formula. Time is just the change in velocity. This is the change in velocity divided by acceleration, for example. Okay, so there's different ways of finding time and acceleration. We'll look at some options. Okay. The nicest thing is if they tell you this object is moving at a constant velocity. What do you know if it says it's moving at a constant velocity in this formula? If they say constant velocity, what can you then before you go into this big formula, replacing work done by gravity, then you can replace something immediately. What can you replace?
Isn't the final velocity is what your initial velocity?
Yes, in other words, final velocity and initial velocity are the same. So what will happen on this side of the equation?
It's gonna be 0.
Change in kinetic energy is 0. If I'm moving at a constant velocity, it means my kinetic energy is not changing. So change in kinetic energy is 0. Does that make sense?
Yes.
For a lot of people, they don't get that. I don't think they understand change in kinetic energy. Change in kinetic energy means the difference between my future and my past. If there's no difference, if it's the same, it means it's 0. The difference between the two is 0. Make sense? Cool.